will be our tool of use in exploring the predictive modeling capabilities of machine learning. So I'm going to take you through a simple demonstration of the general concept of linear regression, and then you're going to implement an actual linear regression model using NumPy alone. Okay, so allow me to present my screen. Okay, so I hope my screen is visible to everyone. So today's focus will be on linear regression. Let me put it here. And for all of you with some basic background in linear algebra, you know there is this famous equation that y is equals to mx plus b. Essentially, what this equation tries to do is that it tries to create a linear relationship between independent features and dependent features in a given set of variables. So our y in this case is the dependent feature, while x is the independent feature. Now, when it comes to, okay, this is a basic equation of line. Equation. When it comes to linear regression, the equation takes a slightly different formula. You can say that y is equal to wx plus b, where w are the weights, and then b is bias, x stands for our independent features, and y stands for our dependent feature. So in this case, this is how the basic formula of a linear regression occurs. So what it tries to do is that given a set of independent variable or variables, it tries to create a relationship between the variables and the output, which is our y here. And then based on this relationship, it can then try and predict new values of y. So having said that, we can conclude, or rather we can infer that linear regression is mostly used for continuous values. Like when using linear regression, you want to predict things like the age, price, maybe salary, and things like those, things that are continuous in nature, not categorical in any way. Okay, so that's the basic intuition behind a linear regression algorithm. So I just quickly want to visualize to you how linear regressor looks like visually. So this is how it looks like. So here on the x-axis, we have our independent features. And then on the y-axis, you have our dependent features. So this is the linear relationship that I was telling you about. So the blue line here is a regression line that is obtained from fitting this equation in our original data. And our original data are these scatter plots. Okay. Just to mention in passing, but later on we'll explain it better, the difference between each data point and the regression line is considered the overall error of our model. We can use different metrics that exist for regression analysis. There is the mean squared error, root mean squared error. I think there's also the mean absolute error and the R squared error. At this point, I'd like to stop briefly and request if anyone has a question so far to bring it up. Okay, fine. If there's no question, I'm going to proceed. Is there someone who wants to say something?
Okay, it is not a question, but I'm just curious on how you have managed the graph in the markdown cell. Can you just take me through?
Okay, first let's start by addressing what Wambulwa has raised up. As I was saying, today's class is exploring the functionalities of NumPy, and particularly we'll focus on how NumPy can be used for mathematical processes such as developing a linear regression algorithm. So the title of this course, of course, is Data Science with Python, and there's basically no way that you guys are going to do data science without first learning about linear regression. So that's why I chose linear regression for this class. So the basic intuition behind linear regression can be inferred from our linear algebra knowledge, where we know that the equation of a line is given by y is equals to mx plus b. So in linear regression, we change this m to w, but basically they're the same thing. Y here is our dependent variable, x is our independent variable, b is our bias, and w is an weight. To make this illustration more clearer, think of it this way, like we have data, say the security of a region, uh, maybe the number of police posts and things like those. And then for every aspect of this data, we have another column or another variable called the price of a house, like the data we were working with last week. So y in this case will be the price of the house, and x are the features that determine the price of the house. So we are attempting to create a linear relationship between these features and the variable, and then using this relationship to predict the price of new houses given certain features or given features that were present in our initial data. So essentially, that is the entire logic behind a linear regression model. And in this graph here, I'm trying to summarize the output of a linear regression model. So once you have developed your linear model here, you can fit it in your original data to see how it has fitted. And so what you're trying to compare in this graph on the x-axis are independent variables, and on the y-axis we have the dependent variable. So this is it, blue line here is the regression line that has been obtained from the linear relationship that we had earlier on created. So just a foresight is that the best linear relationship occurs when this line cuts through most of the points. Not all, but most. If it cuts through all, that will be an instance of overfitting, and you don't want that to happen. So I hope to Wambulwa that is clear now. Sorry, Kevin, let me try adjusting the screen size.
Okay, this thank you.
Okay, excellent. Is there any other question? Okay, I hope none. So, Brian, to address your question, I think I'll share it with you. I'll comment down on the notebook that I'll share with you so that you can see how you can import images to your notebook as a HTML function. So, okay, fine. With that, now we need to understand how a linear regression will actually be tuned to work better. So there's this concept of gradient descent. Let me just put it down here.
Excuse me, sir.
Yeah.
And a linear regression model can only be used when we have one independent variable. Is that correct?
We have a simple linear regression model that works with
Yeah.
one independent variable, and also you have
Yeah.
multiple linear regression model that works with multiple independent variables. So take
Okay.
note of that, please.
Okay, thank you.
Okay, welcome. So we're talking about gradient descent. So basically, gradient descent, of course, here we mentioned that there is an error term between the observed or the actual data point and the predicted point here on the regression line. So our objective, of course, is to minimize this error term such that this regression line is as close as possible to each of these data points. So one way through which we can reduce this error term is through gradient descent. And I'm just going to visualize it to you here because that's much simpler. So in this curve here, on the y-axis, we have cost, which I'm going to call it my error function. And then on the x-axis, we have the weights. And then we have this kind of parabolic curve here. So our objective is to start with a high cost or a high error rate, and then slowly get to this point here, which is a global minimum, where our error rate will be at the least. A low error rate will imply that our model is actually performing well as far as ensuring that this line is as close to this point is concerned. So that's our objective. And to do this, we need to define a learning step, or what some of you may have known as learning rate. So learning rate determines how many steps or how frequently our model will be learning new knowledge. You can set a learning rate to maybe a value of 1 or 0.1. If you set it to a lesser value, it means that our model will take a lot of time and will be taking smaller steps in this curve. And in most cases, that's going to result in better results or better performance. If you take a bigger learning step, your model will tend to go through this entire process much quickly, and in so doing, it may miss out on important parameters during the training process, and subsequently, the performance may not be desirable. So that's all about gradient descent. Then finally, once we've tuned our model, we want to compare, or we want to evaluate how it has performed. So the next step will be performance evaluation. So for regression models, just note it here. Regression models can be evaluated by numerous parametrics. So we've got the root mean squared error, mean absolute error, and I think the R-squared scope. So you're going to read on the root mean squared error, MAE, and R-squared. In this case, we are going to focus on the mean squared error. So let's provide you the formula for the mean squared error here. And here it is. It's basically the average of the difference between the squared value of the actual observation to the predicted observation. So going back to this curve, we are taking this point here as our actual, and then we are going to find the difference between this point and this, square the difference, and then repeat the procedure for our entire set of predictions and actual observations. Then once we find that total sum of square, we do what? We calculate the average, and then that will give us the MAC. So again, up to that point, do you have anyone with a question or a concern? Anyone who is not getting anything clearly?
I have a question.
Oh,
This MAC, is it a formula?
MAC stands for mean squared error, and yes, this is the formula for calculating mean squared error.
So,
Okay.
excuse me. Just a clarification. Why have we just go for the mean squared error? And for example, if maybe you are determining the price and maybe you square dollars, it is in dollars squared, will it work a better way when it is squared? Or can you just tell me why you have decided for the mean squared error?
That's a tough question. I settled on the mean squared error because understanding it is much simpler. So I think what the mean squared error results in, it will show you the difference, or it will show you how far your, it will show you the square of how far your actual prediction differs from, how far the square of your prediction differs from the actual value. Like if I find my mean squared error as 200 or 269, for instance, then it means that my model has predicted with like the difference between my predictions to the actual observations is off by the square root of 269. So basically that's what the mean squared error infers. So to get the actual difference, like the actual difference between observation and your prediction, you use the root mean squared error, which is basically the square root of this. These two tend to provide better results when you're working with data that is far off from the regression line. Like in this case, if you had data points that are scattered far away from this regression line, using the mean squared error and mean squared error would be better because you are actually taking the difference of the squares, and considering that you may have negative differences, taking their square might help in improving the performance of the model. But I would advise you to read more on it to get a clear understanding. This is just a basic overview.
Excuse me.
Okay.
Yes.
To add on it,
Uh-huh.
okay, our teacher also emphasized that when you take the summation of the yi minus the yi hat, it's always equal to 0. Hence, we emphasize on the square of it now. And also, when you take summation of the yi minus yi hat absolute, it is hard to deal with. Hence, it's advisable we use the summation, the squares.
Yes, thank you for that explanation.
Okay.
Do you have anyone else with a question or a concern or something that they would like to share? Okay, I'm assuming that there's no other question. So at this point, I'd like to move on to the implementation of a linear regression model using NumPy. Just a disclaimer before I start the implementation. It's heavily built on functions and classes in Python. So for those of you who don't have a strong background in programming, please don't feel intimidated. For those of you who may have interacted with classes and functions before, I'd encourage you to follow along because I may make a mistake somewhere, so I'll appreciate if someone points it out. Okay, so I think I'm going to start right away. And to do this, since you are implementing it from scratch, I'm going to create a class called linear regression. And then I'm going to create a setup function here. And here I'm going to take in arguments such as the learning rate, the number of iterations that our model is going to iterate here. Those are the only arguments that I'm going to take. And here the learning step here, which, the number of iterations. Okay. So select the learning step. So basically, I have initialized my initial parameters that I'm going to work with in my model. So I may also want to pass in the weights that we have discussed earlier. And then the bias as well. So I think I forgot to mention the importance of weights and bias in this equation. So different features may have different weights. So what the linear regression model that we're going to implement will do here, we'll start with an initial weight that will be 0. Like every feature will have a weight of 0. But as our model trains or as the iterations increase, we are going to update this weight such that it learns from the predictions. The intention is to reduce this weight as much as possible so that also our error function here will reduce. And then we'll also apply the same to the bias. Bias essentially controls how skewed this line might be. We don't want this line to fit through every point here. That will be an overfitting model. Also, we don't want it to be like to just cut across an area with few number of observations. So essentially, that's the purpose of weights and bias. But I'll encourage you to read more on them to understand them better.
Okay, excuse me, sir.
Yes.
Sorry for I have asked my question late. This mean squared error. In our class, we were taught that it is summation of yi minus yi hat squared over 1 over n minus the number of parameters. And why are we using 1/n?
Because
Yeah.
this function inside the summation is the squared error,
Yes.
and then
Yeah.
this 1/n is basically a parameter for calculating mean. I think that should be pretty much obvious. So I think this formula is just correct. Maybe they are the same stories but different scripts.
Okay. Okay.
Yeah. But I would advise that I would request that you share with me that formula so that I see if there are any major differences.
Okay. Yeah, I'll share with you.
Cool.
Or you want it
Yes.
right away?
No, not right away.
Okay. Thank you.
Okay. So we continue after declaring these initial parameters here. Our next step will be performing the fitting function. Essentially, what the fitting function does is that we are taking now this formula over here and applying it to our original observations. So to do that, I'm going to define a function here. And it's going to take those as my arguments. And so what this function will do, it's going to first establish the number of samples or the number of observations in our entire data set and the number of features in each observation. So to do that, I'm going to declare these two variables, number of samples and the number of features in observations. And so that will basically be x.shape. You remember when you are working with pandas data frames, we say that you can basically infer the shape of your pandas df using this shape function. And it's going to return the number of observations as the number of rows, and then the number of features as the number of columns. Okay. So after that, we are going to define our initial weights. So we're going to say that our weights will be essentially zeros, and the shape of these zeros will be, or the dimensions of these zeros will be in accordance with the number of features. That is because initially I'd say that we are multiplying each weight here with a feature. So we want a weight for every feature. So to achieve that, we could create weights that are equivalent to the number of features over there. So to do that, I'm going to create NumPy.zeros here, and it's going to take this number of features. Then the next thing that we are going to declare to establish is the bias that we are starting with. And initially, we don't want to have any bias. We want our bias to be 0. Okay. So once we've done that, now it's time to fit our model. So we'll start by iterating through our iterations because our model has to run through all these iterations. So I'll do this. In range, I think yes. In range. So for every iteration that we are performing, we want to find a value for y predicted. And basically, this value will be the dot product of our x, of the transpose of x. Sorry, the predicted value will be the dot product of x and our weights plus the self bias. Okay, so it will be the dot product. So start with x. And then essentially, this is the equation that I began with. So our predicted value here, which is the y, for the tripred, will be the weights times the x, which is here, plus the bias. So once we've calculated the predicted value, we want our model to learn from these predictions. So the next thing that we are going to do is that we're going to calculate the derivative of these weights and the derivative of the bias, and then use them to update them. You see, initially it started with none, with the intentions of updating them with every iteration. So if we perform the derivation of the weights and the bias, we are going to end up with an updated model. So I'm going to show you that. I'm going to show how we calculate the weights. Derivative of the weights will be calculated by obtaining the average, the average of the number of samples multiplied by the transpose of the number of features and the difference between the observations and the predictions. So I'm just going to do that, copy paste that because it's quite lengthy. So as I was saying, the derivative of the weights is given by the inverse of the number of samples multiplied by the dot product of the transpose of our features and the difference between the predicted value and the actual value. So I'm assuming that you guys have some knowledge on matrices and that you know about the transpose of a matrix and things like those. If you're not familiar with that, I would encourage you to go and refresh your knowledge on it. And then we may also need to calculate the derivative of the bias. So to do that, again, here it is. So the same thing, the average of the samples or the inverse of the samples multiplied by the summation of the difference between the predicted value and the observed value. So once we have our updated weights and bias, we now want them to update in the initial weights that we had provided. So to update that or to do that updating, do this, and then it's the product of the learning step and the new weight. So then the new bias. Okay. So basically what I have done here, these two commands here are basically the gradient descent that we had begun with initially here. So what you're doing is that for every weight and bias, we are trying to reduce it so that we can arrive at this minimum point. And if you look keenly, to arrive at that point, we need to also introduce the concept of learning step, which we had defined initially. So we are saying that we'll be moving in steps of 0.001, and for each of these steps, in each of these iterations, it will be predicting the actual value, and then it will be making a prediction from the given features, and then using these predictions, it's going to update the weight and the bias, and then using the updated weight and bias, going to update the error function such that it's as low as possible, because that's our intended objective. Okay, so once you're done with that, the next process will be making predictions. So we define a function called predict, and those are the two arguments that predict will be taking. So what predict does is that it's now going to take the final value from this iteration here and pass that as our predicted value. So it will be y predicted dot So the difference between these two is that in the fit function, we were iterating through these iterations to update the initial weights and bias that we began with. Now in the predict function here, we are working with the final iteration of the weights and bias, which was obtained after 1,000 iterations were completed. So after getting y predicted, finally this function is going to return y predicted. Okay, so that's it. That's all about the linear regression model. So now we want to test our model using data that we want to generate synthetically. And to do that, we are going to use a function called sklearn datasets. But before I continue, is there anyone with a question?
Okay, in the class linear regression you have created, is it available in any of the libraries within the Python? We have to create it from scratch the way you have done?
No, you don't have to create it from scratch. It's available in, let me just put it here. So linear regression is also available on sklearn. So we just use sklearn.linear models, and you'll find their linear regression. I only wanted to do this so that I could show you how how NumPy can be used to perform mathematical manipulations or operations.
Okay, thank you.
Is there any other question or concern? Okay, fine. I'm going to assume that there's no question. So I'm going to move on to the next step. And the next step involves creating synthetic data that can then be used to compare or to evaluate the performance of our model. But before we move to that step, I want us to implement a function here that will be used to calculate the error score of our models. Because now we have a model, we need to evaluate it. So I'll create a function, evaluate model, and it's going to take into arguments the y and the predicted value. Is actual predicted. So the output of this model, of this function, will be basically what we've discussed here. So it's going to be the mean of difference of the square. Let's see, actual and predicted squared. Okay. So to create our synthetic data, use the dataset function. I'm using the make regression because our problem is a regression problem. The number of samples in our data here should be not much, maybe 1,000. Then we can introduce the random step first. Okay, and then before I continue, I need to import this as well. It's always good practice when you're working with machine learning algorithms to split your data into train and test sets, train, test, and validation sets. So the importance of that is that you may use the train set to train your data, and then to evaluate the performance of the data, you can use the test set. So to create that, I'm going to say that my test size will be 0.3, implying that I'm going to use 70% of my data for training purposes and then the remaining 30% for testing purposes. And I'll demonstrate. Okay. So now that we have everything we need, it's time to call this class over here, perform the fitting, make the predictions, and then evaluate the performance. So I'm going to call it.
Excuse me, sir.
Yes.
On the XY dataset make regression,
Uh-huh.
what is the purpose of that parameter for the noise?
Noise is
The
just
noise.
to make it random. We don't want our data to be uniform in any way because it may not be appropriate for a linear regression model. We want some noisy data such that fitting a linear model may be a little bit tough or problematic. I don't know if I've answered your question. Hello?
Okay.
Okay, fine. So I'm going to assign the variable name model to my class. So then the first step will be to fit my model into the training data. Then finally, to make predictions, I'm going to call my predict function in my test data. Okay, so it's done already, and I think we can check out some few predictions. There they are. So nothing meaningful yet. Just to do some space. And finally, if you want to compute the error score of our model, you can say that the error is evaluate model, and the functions, the arguments that will be taken in will be the predictions. We'll start with the y test first. The predictions. So if I call my error, it's going to give me 7,452. So essentially what this means is that if we take the square root of this value, it will be the difference between what has been predicted and the actual value. So the actual value and the predicted value differ by a value that is the square root of 7,452. Or the way someone had asked earlier on, consider the root means that there will be the NumPy square root. So the actual value and the predicted value differ by a value of 86.3279. Yes, so basically that's everything about linear regression in a nutshell. But this is a very, very basic implementation of the algorithm. And it was aimed at exploring the different functionalities of NumPy. If you look keenly, we have used the zeros function that I discussed earlier. We may decide to initialize our weights here with the value of ones or fours. So that's one way in which NumPy is being used here. And then to actually fit the algorithm to our data, we had to use the dot function, which I believe we had touched on earlier. So another function that has been used in NumPy is the sum. It's been used to update our bias. And then, yeah, finally, the last thing was calculating or creating an evaluation metric. Here, the main functions of NumPy used are the mean function and square root function. So I think that should be a comprehensive overview of some of the functionalities that NumPy provides for different data science tasks. At that point, I'd like to invite any other questions if you have any.